Hi guys, today we're going to talk about chemistry and light. And as you look at these pictures, they all have something in common. And they actually all have something to do with chemistry, but they all radiate light. As a stove eye gets hot, it radiates light. As iron gets hot in a fire, it radiates light. And obviously the sun radiates light. Fireworks radiate light, and we're going to talk a lot about fireworks as we go through this podcast tonight. Right. There are a few things you have to understand with a ladder. You can climb up the ladder. Once you climb up the ladder, you come back down the ladder. All right, so what goes up comes back down, and when it comes back down, you're giving back energy because it takes energy to climb the ladder, but you give it back when you come back down. You're allowed to step on certain stairs of the ladder, okay, but you are not allowed to step in between stairs. So you're not allowed to stand halfway up a stair. That just cannot happen, okay? So you may go up, you may come down. When you come down, you give off energy. When you go up, you take energy. And when you climb up these stairs, you may go up them, you may come down them. When you come down them, you don't have to come down them one at a time. You can jump down them two, or you could conceivably jump all the way down to the bottom if you wanted to. All right? So that's important to realize as well, because we're going to relate all of that to electrons. Okay. Let's look at lithium. In lithium, you have 3 electrons. You have 2 electrons at the 1s level, and you have 1 electron at the 2s level, right, where n equals 2 because it's at the second energy level. Now, when that electron gets heated up, like I could add electricity to it, I could put it in a fire, but when that electron gets heated up, it gets excited and it moves away from the nucleus, and it can move 1, 2, 3, or more levels away from the nucleus. Eventually, when that lithium atom cools down, those electrons will fall back down to where they started. And they can fall back directly from the second level to the first, or the third level to the second, fourth to the second, or fifth all the way to the second. Or potentially, it could only fall back part way, and then it can fall back the rest of the way eventually. Or it could fall back 2/3 of the way and fall back that way. Same thing is true from here. It can do this in multiple steps. That's the concept of the electron. When it goes away from the center of the atom, it is absorbing energy. And when it falls back down, it is releasing energy. And when it releases energy, it releases it in the form of light. And that's why you see a stove, the red eye of the stove, giving you light. Now, there are different colors and different wavelengths that you see when things are at different temperatures. And this all has to do with quantum theory. So you have red hot, yellow hot, and white hot. So why do different metals give off different colors? We'll talk about that. Why do stars give off different colors? We'll talk about that too. Max Planck was around in 1900, and he was a German physicist, and he was able to predict accurately how the spectrum of radiation emitted by an object changes with its temperature. Notice the word predict, right? That is what was so cool, was he was able to predict what would happen. Remember, we talked about that earlier with Mendeleev, of prediction really is important. And he suggested that the energy emitted or absorbed by an object is restricted to pieces of particular sizes, which he called quantum. Now, I will often use the word quanta when I'm talking, and quanta is simply the plural of quantum. So just don't be confused, you'll hear that term as we go along in the podcast. A quantum is the smallest unit of radiant energy that can be absorbed or emitted. So originally, it was thought that energy was infinitely variable. And what Max Planck came up with was the concept that it is not infinitely variable. There's a very, very, very small amount of energy, okay, that is a quantum. So it's just a chunk of energy. So where do we use chunking? Well, we use it in money. For example, for a parking meter. If someone needs a dime for a parking meter, it's got to be a dime. If someone wants a piece of gum and it costs $0.25 for the machine, you have to have $0.25. So if you have $0.25, you can get a piece of gum. If you have $2.25, you can get 2 pieces of gum. All right? What happens if you have 25 pennies? Can you get a piece of gum? Nope. How about you have 100 dimes? How about you have $100? Can you get a piece of gum? No, because the gumball machine only takes quarters. So you have to have exactly $0.25 to get a gumball. The concept is the same with an electron. The electron is going to absorb a certain amount of energy, and it has to be a discrete amount of energy, just the right amount. And when it gives it back, it's going to give back exactly that same amount as it falls back down. Okay? So it has to be just the right amount of energy. We do this all the time. We do this with money. The smallest unit of money we have is a penny. When you go to a restaurant, can you say, I want half a waffle for breakfast instead of I want a waffle for breakfast? Can you go to a grocery store and get half a box of Cheerios or half a can of soda out of the vending machine or half a bag of popcorn? Or go into Walmart and say, I want a quarter of a piece of paper? Or can you go and buy half a pen? None of this makes sense, right? So these are all examples of where we use quantities of things in our lives. Remember, the electron does the same thing. Digital music is another example. We think we hear continuous sounds. Back in the old days when we had records, those big black things, we had grooves in them, right? We didn't have numbers. Now we have small little CDs and they have numbers on them, right? And our ears are not good enough to detect the small differences in the sound when the numbers change. Okay? But that's because our ears aren't good enough to do that. But there are small changes. What happens if I want to get between two numbers? I can't do it. What happens if I want to get between two notes? I can't do it because there's no way to do it. Changes in energy work exactly the same way. So, when I have an electron, when it goes up, when it goes away from the nucleus of an atom, like here, you'll notice that it is absorbing energy. When it falls back down, it's giving up energy, and it's emitting a photon. It gives that off in terms of light. When it falls back down, that energy level. That's exactly what's happening with fireworks. Let's think of fireworks, for example. When you think of fireworks, if all of the light happened when the atoms got hot, when the explosion happened, then you'd see all of the brightness right in the middle of the fireworks. But you don't. What do you see? What you see is the firework exploding, and then way out here, it's giving off light. Why is that? Well, it's giving it off as the atom cools down. As the atom cools down, the electron falls back to where it started. When it falls back to where it started, it gives off light. And this light is now what you're seeing. And that's why the light is not centered right in the middle. It's all around the outside. So we have a couple of equations we need to be familiar with. The first one is right up here. And it says the speed of light is equal to the frequency times the wavelength. You should be able to look at that and say, well, that means if the frequency goes up, the wavelength has to go down because the speed of light is constant. It's 3 times 10 to the 8th meters per second. It is constant. And remember, when we're looking at light, we're only looking at a very small piece which is visible. So when fireworks go off, they're probably giving off other light that we can't see. It's up in the ultraviolet range, or that's down in the infrared range. So that's possible as well. Now, Planck's theory is it deals with the relationship between the frequency of light and the wavelength, hence the wavelength, because we know that frequency and wavelength are inversely proportional. And we're looking at the energy with which it is associated. Now, we have this equation here. Energy is equal to Planck's constant times the frequency, which tells us that when energy goes up, frequency goes up. And this is Planck's constant, and you'll notice it's a really, 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 really small number, times 10 to the minus 34, right? It's a really small number. So the energy is really, really, really small, okay? And we know that nu is frequency. Now remember, we can determine wavelength from frequency with this equation down here, okay? So the higher the frequency, the higher the energy. They are directly related. So think ultraviolet light, higher energy, versus radio waves, lower energy, right? So hence, higher frequency, lower frequency. So how was Planck's theory used? Well, it was used to determine the temperature of distant planets and stars by measuring the wavelengths of electromagnetic radiation. That's light, right? We like to call it electromagnetic radiation because it's not just visible light, it's all light, including stuff outside the visible range that these bodies would emit in space. So that's what we looked at. We looked at the light that was emitted. And Niels Bohr was the first to see the connection between the wavelength an element emitted and its atomic structure. And so what he did was he studied hydrogen. Why did he study hydrogen? Well, because it's simple. And he knew it had one proton, which really didn't matter. And it had no neutrons, so those clearly didn't matter, because all he was focused on was the one electron. And he said the energy of that electron must be quantized. It must absorb or emit energy in certain quantum. So he knew about certain orbits. Remember, this is Bohr. And so he said that the electron could only be in certain orbits. We now know they're orbitals, but it doesn't matter. And they are corresponding to different amounts of energy. Orbitals do follow the same principle. So his concept was that as this electron moved up, it was going out because we heated it up or we gave it energy, electricity, whatever it is, and when it fell back down, it would give off light. Well, they found out that when it fell back all the way down to its ground state, which is down here, it gave off ultraviolet light. When it fell back, instead of to level 1, when it fell back to level 3, it gave off infrared light, which was nowhere near as powerful. Frequency was less, energy was less. But when it fell back to the second level, it would give off light that was actually within the visible range. And in fact, they saw these lights down here. And so what we're going to, and you'll notice that there's certain frequencies of light, like this red light and this blue light, and you'll notice there's nothing in between. It gave off a certain frequencies of light. So we're actually going to do this. We're going to take some hydrogen gas, and we're going to heat it up in a little tube right here, and it's going to get very hot, and it's going to give off a lot of light, and then we're going to run that through a prism, and we're going to see the different line spectrum that we can see coming out of it. We're going to see the fingerprint for hydrogen. Okay? So we're going to watch that in a video right now.
Okay, folks. So here what you see, this is a, let's try this again. Hi everybody. What you see here is you've got a hydrogen spectral tube, meaning that inside this tube there is only hydrogen gas. So to the naked eye it looks kind of purple, kind of a reddish purple magenta color. All right? But when we go and we put a filter in front of it, specifically this prism, what you're able to see is you're able to see how the different colors, what works best up there, all the different colors spread apart. So you can see a red line and the aqua line really well, right? So you get an idea that it is actually split up. I actually see a second line out there, but it's a very purple line, I think, but it's really hard to see, right? So that's the spectral tube for hydrogen.
All right. So let's take another look at an atom. That should have been pretty cool. The line spectrum is the spectrum that contains only certain colors or wavelengths. And that's what you just looked at. You just saw certain bands of light. Right? And elements emit light when they're vaporized in an intense flame, meaning when they're burned. And you're going to see that as well. You're going to do that in a separate lab. And when you see that, you're going to see different colors. So for example, you might see one that's red. Lithium, for example, gives off red. But so does strontium, I think. And as a result, they're hard to tell the difference when you just look at them with your naked eye, right? Sodium gives off yellow, for example. So each one gives off a unique color. But with our eyes, it's kind of hard to tell. But when we run them through a prism, we see all of these different lines. And that's what these things are called. These are called line spectra, where we see the different lines. So if we look at lithium, for example, we see these different lines. Red is the one that's really, really bright over here. Now, when we look at sodium, we see these very two distinct bright yellow lines, and you'll notice there's very little else out here. All right? And potassium has two yellow lines that are very similar. In fact, it actually has three yellow lines, but they're very similar to where sodiums are. But notice we've got other lines as well out here for potassium that we do not have for sodium. Okay? So each element has its own unique fingerprint and its own unique set of lines that come up that when you heat them up. So how was helium discovered? It was discovered during a solar eclipse. And they were looking at line spectra and they found some new ones. Okay? So when you look at hydrogen, here's hydrogen's line spectra, these special lines here that you see for blue and red, excuse me. But notice for helium, you've got this bright yellow one in the middle, as well as a red one, which is pretty close to the other red one, and some blue ones, which are pretty close to hydrogens. They are different. Okay? But you also have this yellow one in the middle. Everything is unique. So what we're going to do is we're going to look at a bunch of different colors, a bunch of different line spectra.
Okay, folks, here we have the spectral tube for helium. The spectral tube for helium, notice, has a completely different color to the eye than hydrogen had. And when we put the filter up in front of our eye, we notice that we have some very bright red lines and yellow lines and green lines. There's a magenta and a blue line in here, but they're completely different than what you saw with hydrogen. So just wanted to make sure that you saw how different it was of what the actual colors are that are coming from helium. And notice the black in between the red and the yellow and the blue. That means there's no orange, for example. So that's a color that helium just does not give off. Okay? Here's argon. To the naked eye, it's a very purple magenta light, kind of like hydrogen was, but not as bright. When we put the filter in front of us, we can see some red, very clear red, and some orange and some green, some distinct patterns there. We also have a very deep purple that's there that you should be able to see. Again, I'm not sure what's coming through on the video, but that's what I can see with the naked eye. Alright, this is krypton, a noble gas. I feel like I'm up with Superman. It's just a pure white light as far as my eyes can see. But when I put this in front of it, you should be able to see very distinct green, yellow, and red lines with a slight purple way out to the edge. So you get very distinct bands of color and very distinct missing bands. Here we have the spectral tube for mercury. Kind of looks bluish purplish, and when we put the filter in front of us, we notice some seriously bright red lines, a couple of orange, couple of green, blue, purple. Okay, but again, you'll notice there are separations between the lines, so there's not much orange in there. There is a very bright red, and there's a very bright green. Kind of gives us that purple look. Okay, that's mercury.
Alright, neon is my personal favorite. Unfortunately, I can't show you neon because it didn't come up on the... I tried with the camera, it didn't come out. If you want to see neon, please just ask me in class or ask Ms. Sherman in class. We'll be happy to do neon for you. Neon's really cool. It's got lots of bright red lines. Okay, so in summary, atoms absorb energy in quantized units. We call them quanta or quantum. Atoms release energy in exactly those same units. So whatever energy you put in, you get exactly that same amount back. Different atoms absorb different quantities of energy. Why is that? Well, because they all have different orbitals. They all have different numbers of electrons that are held in by different numbers of protons holding them in. So it always takes a different amount of energy for every element, and that's why they're all unique. And that's why each element has a unique signature, different line specters. Remember that higher energy means you have higher frequency, shorter wavelength. Examples would be ultraviolet rays, X-rays, gamma rays. And lower energy is lower frequency, and that's the opposite end of the spectrum. They have longer wavelengths, things like infrared light, microwaves, and radio waves. All right, folks, that's it for this podcast. If you have questions, see me in class, and see you later. Have a great day. Bye-bye.